So, hello everybody to the statistics lecture, and today, after we have already analyzed in a descriptive way some data we have created so that we calculated the measures for averaging our data, calculating different means, and then also calculating some measures which are measuring the dispersion, and in the end we calculated also the so-called contingency table. And actually I think one of you chose the ninth topic, and this topic is about this chi-square test when you are want to analyze the dependence between two variables. Okay, but then before we start in this lecture with the so-called hypothesis testing, I just want to go with you through a little revision of the basics of statistics. So in general, we are dealing with so-called random variables, and these random variables, they are just mapping our sample space. So to speak, what is happening into the real numbers, and what is the what are we doing with these real numbers? With real numbers, we assign to our single events some probability. So that in the end, we have our sample space. There we have our events A, and that now we have a mapping P of A equals the probability that this single event happens. This is the general definition of our random variable. And there also, if you look in textbooks, we are distinguishing between the random variable, which we assign in capital letters, and then if we have our definite outcome. So to speak, our random variable is the color of your eyes. And this can be blue, green, brown. What else? So our sample space are the different colors. And then if we look at one person and then we see this person has green eyes, then this green event, for this, if we know that this person has green eyes, this we call then the outcome, and for this we assign small letters. So there you have to be a little bit careful that you do not interchange random variables which are assigned with capital letters and then the definite outcome which we assign with small letters. Yeah, well, and what are we doing with this random variable? There we can say that in every random experiment, we think that we can express such a random experiment via a random variable. And there, I think you have done this also in your introductory courses. The classical random experiment is just throwing dice. And there, then we know that our sample space is the outcome of the numbers which we can see in the end after having thrown our dice is 1, 2, 3, 4, 5, 6. This is our sample space, and here we assign this with capital X. So capital X can be the number 1, 2, 3, 4, 5, 6. And then after having thrown our dice, then we see, well, that we find that the 5 dots are be seen, and then this is a realization of our random variable. So this is the realization of the random variable. And now we have our mapping from the sample space omega into the real numbers that we can now assign for the event. And what we define as an event, this is up to us, what we are interested in. So we can, of course, assign an event as seeing the number 5 and then asking for the probability of the number 5. For this, of course, if we have a fair dice, then the probability is 1 over 6. But we can, of course, also say that we are interested in the event that throwing a dice shows a number smaller than 5. And then we ask for our mapping, what is the probability that our dice shows a number smaller than 5? So this means what is the probability that the dice shows a number smaller than 5? Yeah, this is my question to you. If we have a fair dice, what would be then the probability? Which number? This is our event, which we defined. Number, oh, this one, number smaller than 5. 2 over 3. Yes, because we know every single event has the probability of 1 over 6. And then we say we need the sum of the probabilities of these 4 possible single events that our dice shows a 1, 2, 3, or 4. So this is then the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4. And this is then 4 times 1 over 6 is 2/3, of course. Okay, But now also in statistics, we are dealing with different kinds of random variables and making this experiment, throwing a dice or flipping a coin, then we say that this is a discrete random variable. And then we can say that our sample space is finite in the case of the dice, 1, 2, 3, 4, 5, 6, or flipping one coin. There we have heads or tails. But taking this experiment flipping a coin, we can also define another experiment, and another experiment by flipping a coin would be that we say we are flipping the coin n times or even up to infinity in a row. And this means still that our sample space is not finite anymore, but it is still countable. So we can say flipping in a row 3 times a coin, or 17 times, or a million times. And this we can increase to infinity, but still it's countable. But what we also can do, and remember our descriptive example with which we have started, there we said, well, we choose as the random variable the length of the student. Well, and this random variable, the length of the students, this is not countable anymore. Because why? Well, it's measured in centimeters. And there, the definite length of some guy can be any number with an infinitely large number behind the dot. So our length could be 172 centimeters, 0.128756, and so on, and so on, and so on. And for this, we say the, for example, length of the students. Oh, you can see this. And this length of the student, this is element of the real numbers R. Well, and the characteristics of the real numbers R is that you cannot count them. So there is no direct mapping between the natural numbers 1, 2, 3, 4, 5, 6, 7, 8, 9 and the real numbers, which can be every number with every row of numbers behind the dot. So real numbers are not countable. So this means there is no direct mapping between the natural numbers n and the real numbers R. So you do not find a mapping that 1 coincides with the first real number, element R, 2, some second number, element R, and so on. This does not exist. Well, and what is the consequence of this uncountability of the real numbers? But we are, of course, interested in such random numbers. This means there is no interpretation anymore in the question, what is the probability that the length of a student is some definite number? Because it could be just slided away by 0.000001. So we cannot interpret anymore the probability of some guy which has the length of 172 centimeters. But what we now are doing is that we are assigning a probability to the realization of a random variable within some interval. So this means no probability of some specific single number, but probability of the realization of a random variable within some interval. So we can pose now the question, what is the probability that our random variable x lies between two numbers, maybe 172 up to 173 centimeters. Well, and I think you have, of course, dealt in your introductory course with these discrete random variables and with continuous random variables. And for this, we, so to speak, have some different representations, because now, as I said, we have no probability mass function anymore, because there is no interpretation of probability that a guy is exactly 172 centimeters, because this random variable length is chosen out of a sample space omega, which we cannot count. And therefore, we go from the probability mass function to the so-called density function. And this is mostly represented as small letter f of x. Maybe can you give me a feedback that you also have talked in your introductory course about these density functions? Is this true? So the term density function you have already heard, hopefully also in school. Well, I have already talked in the beginning, not sure, but this density function, the density function which you know hopefully is the normal distribution, and this looked like this. But then, of course, you cannot say that, let's say here is the number 3, that now the number 3 has the probability of this number you find here. But what we now interpret is that we maybe have here an interval from 2.9 to 3.1, and then the probability that x is within the interval 2.9 up to 3.1, then this probability is the area under the density function within the interval. This interpretation, hopefully, or this definition, hopefully, you have already seen. Oh, so let's see here. This I have to put a little bit on the side. That you can see this. So anyway, we will actually deal a lot afterwards when we are talking about hypothesis testing with this interpretation. Yeah, and then remember our short question: what is the probability that our dice shows a number lower than 5? This we can also translate in the event. What is the probability that our dice shows a number equal or lower than 4? And then, of course, what we have done is that this probability p of x lower equal 4 is just the sum of the single events. If we have a discrete random variable, and this is called the so-called cumulative distribution, and then see what we do here in mathematics. Then we interchange our summation operator with the integral operator. And hopefully from school, you know that, yeah, this sign here should represent something like a stylized capital S for a summation, because this is interpreted as the area under some function. And here, as I have shown you, this is then the area here under the density function, and the cumulative would be then that we start with the lowest possible event, and in general the lowest possible event could be minus infinity. Of course, we could have also other distribution functions, the density functions, for example, for the uniform distribution, or then the density function would just look like that we have some number within some interval, I low and I upper bar, lower bar and upper bar, and at all other parts of the real numbers, our density function would be 0. Well, and then, so to speak, here we are start summing up probability of our dice throwing a 1, throwing a 2, throwing a 4 is now starting from the left part. Let's do this in red and then calculating the interval up to some number x. Yeah, and then remember our introductory example where we calculated some averages. There we also then in general define the expected value, and the expected value of our random variable for a discrete random variable is just the single event times its probability and summing up all these probabilities. Well, and so to speak, quite often we take the arithmetic mean as an estimator for the expected value, because why? We assume that all single events are independent and all single events have the same probability. Well, and if these p of xi are all the same numbers, then we know that the overall sum of all these numbers has to add up to 1. And if we have n single events, then of course this probability is 1 over n. And this 1 over n we can put outside if this is 1 over n. And then you end up, of course, for the expected value as an estimator with the arithmetic mean. So quite often we use the arithmetic mean as an estimator for the expected value. Well, and again, interchanging the summation sign with the integral. And now we have to integrate over the whole sample space from minus infinity up to infinity. And we are interchanging here our probability mass function with the density function, multiplying with our event and calculating the integral over the whole sample space. Yeah, and then in general, we are interested in the, so to speak, most important mass for dispersion, and this is the variance, and the variance is defined as the summed up distance, a squared distance of every single event with respect to the expected value. And in our example with the length there, we used for the expected value as an estimator the arithmetic mean, and then we just calculated the variance as the sum of our single events minus the arithmetic mean, and we have squared this. And later on, we will talk about also the reasons why we are using this squared distance. Well, and again, we are interchanging the summation sign with the integral, interchanging the probability mass function with the density function, and here again we have the squared distance with respect to the expected value. Yeah, and then we have some rules. What happens to the operators, the expected value operator and the variance operator? And of course, the expected value of a constant, so not of a random variable, just of a constant, is the constant itself. Well, and some constant is of course not fluctuating, so the variance of a constant has to be 0, since a constant is not fluctuating. Well, and then especially the expected value operator has the property that if we multiply every single event with the same number, with the same constant, then we can take this constant outside the expected value operator. Well, and this we directly see here. So if we put in front of here, this x and a, and we are defining a times xi as a new random variable xi tilde, then of course from our calculation properties of the summation operator, this means then that we can take this constant number outside the summation operator, and this hopefully you also have learned when you have dealt with integrals in school, that you can just move outside the integration process a constant. Nothing else means it that we here can move outside this constant. Well, looking at the variance, we have some different rule, because the variance is defined as the squared distance with respect to our expected value. Then we see here expected value means, oops, let's take again red. This would be here that we have not xi, but a times xi for every xi. We have already shown that the expected value translates into a times mu, and this then means that this we can write as a squared times xi minus mu summation. And again we have the rule with the summation operator that now if a is a constant, then of course also a squared is a constant. So let's put this outside the summation operator, and the same we have here. A squared integral x minus mu and also a squared is a constant, so we can move this outside the integration process. And this means that if we multiplying any random variable with a constant, the variance translates in squared the constant times the variance of our original random variable x. So this means here we have to take outside an a squared. And what else? Well, now we can take this property and this property together and ask what happens to our expected value if we linearly transform our random variable. So this would be then a random variable x tilde equals ax plus b. Well, we know that a constant, the expected value of a constant, is the constant itself, and we know that we can take outside the multiplied constant, and this means that the expected value of a linearly transformed random variable translates just in the linearly transformed expected value of the, oops, this should be a capital X, sorry, this is wrong, the expected value of the original random variable. And then you have to be a little bit careful if you pose the same question, what happens for a linearly transformed variable to the variance? Then, of course, we know a constant itself added means, so to speak, if we take again the length of the students as our random variable, then of course we can add to all these numbers 30 centimeters, for example. This of course means that our outcomes of the random variable now only fluctuating around a number which is 30 centimeters larger than the original point of the fluctuation. But the size of the dispersion of our random variable is, of course, still the same. And what else can we do? We can measure our length in centimeters. Then we have around, let's say, around 170. Or, of course, we can measure our random variables in meters. Then we have 1.72, 100 times smaller. And this now means that our variance gets smaller, but not by 100, but since it is the squared distance, 1 over 10,000. So to speak, our shift to the right or left of our random variable, this vanishes. This doesn't change our variance, but if we multiply our random variables, then we have the to multiply our variance by the square of this multiplication factor. So I hope that this you also have seen in your introductory courses, because this calculation rules of variance and expected value, this is quite often used when you want to show something in statistics. Yeah, and then some time is left. We want, so to speak, start from the very beginning in statistics that in the beginning of the 20th century, there were some clever guy from Russia. He is called, or his name was Kolmogorov, and he, so to speak, defined from the as an original concept what is statistics about, and this are nowadays called the so-called probability axioms, and these are related to Kolmogorov. Well, if you look at the topics, I think there was also one topic. Well, no one have chosen this from you. This was called the so-called Kolmogorov Smirnov test. This is a test on the of the. This is a test in general for distributions. Well, the first axiom is that every single event has at least a non-negative probability. Of course, a single event can also have the probability 0. So throwing the number 7 with the dice has the probability 0. And then, very important, this always you have to keep in mind, if we take the probability of the realization of our random variable, that this can be the whole sample space, then the probability mass of this has to be 100%. So summing up all 6 events by throwing a dice means 1 over 6 plus 1 over 6 plus 1 over 6 times is then the probability 1, and this is the so-called certain event. We know that our random variable is chosen out of the probability sample space, and then we have a probability of 100%. And then very, very often for the single events, we assume that the single events are independent from each other. And then, as axiom 3, we define the event of A and B happening together is just the sum of the two single events. This we used when we said the probability of throwing a dice with a number smaller than 5 is just the sum of probability of 1 plus probability of 2 plus probability of 3 if our events are disjoint. So if they are independent. So that this is the empty set. So, and using these 3 axioms, and this is quite astonishing, we only need these 3 axioms, and out of these 3 axioms, we can build up the whole statistical theory which we have nowadays. And the first one now is if we have events which are not disjoint. So now A and B can be not disjoint, then from our 3 axioms we can deduce the first rule that now the probability is P of A plus P of B minus the probability of the set A and B happening at the same time. So this is the set A with B. And then, if these two events are not disjoint, then we can also the question, well, what is then the probability that A happens but not B? And this is written with this backslash. So probability A without B. So A happens, but B should not happen. And since we have some overlap, or we could have some overlap between A and B, this means then that we obtain the probability of B minus the event when A and B happening together. And the last one is the complementary event. So the event, the probability of the set that our random variable is in between omega, the whole sample space, but not in a subset A. So not A equals the set omega without A. And this is the so-called complement of A. And this is also quite often used when you want to show something in statistics, because sometimes it is quite hard to calculate the probability of some set A, but it is even much more much easier to calculate the complement of A. And then, of course, if our events are not independent, then we can ask for the so-called conditional probability. And this means, so to speak, in a row during time, we say what is the probability that A happens if already B has happened. So to speak, using again our introductory example of the length, there we then introduced, after the length, a second variable, and this was to be male or female. So A is chosen out of the sample space of the length of people, and overall mankind can have a length between 1 meter and 2.50 meters overall. And then we can ask, well, what is the probability to have a length within the interval 1.60 meters to 1.70 meters under the condition that I have a female person. And this is written with this vertical line. So this means conditional probability of A that B has already happened. So this means what is the probability of A given B has happened. Well, and from our axioms, then we can show that this conditional probability is the probability of the joint set of A and B divided by the probability of B. And from this, we can deduce the famous Bayes theorem, that this can be rewritten as the probability of A conditioned to the end event of B is equal to the probability of B conditional on A times A over probability of B, or maybe then one can remember it a little bit easier if you write it like P of A conditional on B times probability of B, and then you are interchanging just A and B. Probability of B conditional on A times probability of A. And here again, I think these rules you have already seen in school, and that you hopefully have seen Bayes' theorem in your introductory courses. Because this, of course, is very, very often a problem in statistics that we are interested in conditional probabilities. Bayes' theorem, these conditional probabilities, have you talked about this in other courses? Yeah, good. So, and yeah, some minutes are left. So then let's calculate some numbers. Given the probability of A is 50%, probability of B is 30%, and A and B probability 20%. What is then the probability of P together with A? Which rule can we use? Well, let's have a look. And I think it is here rule 1. So let's use this one. And then we have P of A is 0.5 plus P of B is 0.3 minus 0.2 equals 0.6. P of A conditional on B. For this, we have our definition of conditional probability. So this would be this. And we obtain A and B is 0.2 and probability of B is 0.3, so 0.6. And C, now it is maybe a little bit more interesting because this is not a direct application of our rule. So what is this? This is the complement of the probability of A and B. So for this we have to apply two rules. So we have here our conditional probability, not conditional, our complementary probability. And where do we find A and B? There we have again rule 1. This we have here. And so this one, using this rule, we can say the complementary probability of A and B equals, with this, 1 minus the probability of A and B and A and B. Oh, sorry, we have directly this one. Then we don't need this one. And here we have directly our 1, 0.2, so 1 minus 0.2. Drawing here. 0.2 equals 0.8. And the last one, d p of A without B. And there we can again directly apply our rule number 2. And this would be then P of B is 0.3 minus 0.2 equals 0.1. So, and then we want in the end today also come to our statistically independent events, and from this we can then calculate the so-called total probability. So first of all, if A and B are statistically independent, then of course it doesn't matter if we formulate a conditional probability. If A and B does not have anything to do with each other, then of course for the probability outcome it doesn't matter if we ask for the probability of A or for the probability of A and B has already happened. Then, of course, P of A conditional on B is the probability of A itself, and of course, the other way around. And then from the definition of conditional probabilities, see this one here, we can, of course, then rewrite this, that this is P of A, and then multiplying with P of B, we obtain that the probability of A and B is just the multiplication of the single events. And this, I think you have done in your introductory course, that you said every coin flip is independent from another coin flip, and this means flipping the first time, obtaining heads has a probability 1/2, and then asking what is the probability of the joint event obtaining heads in the first row and heads in the second row. Every single probability of a coin flip obtaining heads is 1/2. So the overall probability obtaining 2 heads in a row, flipping a coin twice, is 1/2 times 1/2. And yeah, let's at first use for today this definition of total probability. Up. Where do I have the total probability? Didn't I have defined it here? I think I missed the definition of total probability. Do I have it here? And where is it? Here it is. Sorry. This we need. That with this assumption that every single event in our sample space is statistically independent from each other. So we say our overall sample space consists of k disjoint elementary events. Coin flipping means every single coin flip is our single event, or throwing a dice. Every single event is obtaining 1, 3, 5, 2, and so on. This we call then the elementary events. And then using P of A and B, or P of AI and AJ equals P of AI times AJ, then we can say we can calculate the probability of some specific outcome as the sum over the product of the conditional probability that B happens given every single elementary event times the probability of the single event itself. So this is the so-called total probability. And now I'm running out of time. And as a homework for Thursday, I have here two little examples. And with this, we will deal then on Thursday. Maybe you can have a look over the next 2 days into these examples. So, thank you very much for today and hopefully see you on Thursday.